And so we are going to look at the development of the range equation. And the range equation, of course, was designed. The purpose of the range equation is to determine how far something that is shot out of something will go. And of course, we did all kinds of crazy things. This was actually the development of physics, because we used to believe like that things would come out of cannons and they would go so high and then eventually they would just fall down. Eventually, we did discover that it went in this parabolic arc, and the range equation became part of our culture and heritage. Here are some of the things. The vertical distance is 0. In other words, it leaves at the same height that it lands at. And we've looked at examples where the vertical height actually changes. This is a specific case of this. The change in time, we don't have any idea. The acceleration in the y direction, we are going to know that. I am just going to leave it as the acceleration. And rather than use negative 9.8, we'll leave it as acceleration so that we could do this on like an asteroid or Mars or Jupiter. We could export our evil wherever we want to go. Delta dx, of course, that's exactly what we want to know. And so we are just going to develop this equation so we understand where it comes from. Same thing. Delta dy is 0. We're not sure how long it's in the air for. And so if we want to know the time that it's in the air, that will tell us how long it's going to be traveling horizontally. And that's what's important. Okay, so we are going to use the all-star equation for this. And so vertically, because that's how I find my time, delta d equals v1 times t plus 1/2 at squared. Now, I have left off all the deltas and all the arrows and things like that just to try and make this a little bit simpler. Delta d we know is 0. v1 we are going to know what that is. And in order to get the vertical displacement, we are going to multiply that by the sine of theta. And then times the time, which we don't know, plus 1/2 acceleration, which we do know, times time squared, which we do not know. Okay, now you'll notice that this is starting to set up like a quadratic. What I'm going to do is I'm going to factor out time from both of these parts of the expression, vi times sine theta plus 1/2 at. And so there's my equation. Now, I already know that when t is 0, this expression is 0. So t solves this when time is 0. But I also know that this is being fired from the height it's being fired at. And so that's a silly solution to this. I am just interested in the second part. So the initial velocity times the sine of theta, in other words, the vertical component of velocity, plus 1/2 times the acceleration times the time, has to be equal to 0. Okay, what we want to do is get the time that this is in the air for so we can figure out how. So let's rearrange this equation for delta t. So let's move and the velocity in the x direction is just the initial velocity times the cosine of whatever the angle is, and the change in time is given over here. We've calculated this, -2 vi sine theta, and this is over whatever the acceleration is. Okay, we can simplify this a little bit. This is vi squared, and I'm going to put my negative there, 2 sine theta cos theta. And so we can rewrite this as -vi squared times sine 2 theta over a. And in this case, acceleration is going to be negative because it's down. And so depending on how you want to treat that, acceleration, the sign of the acceleration, this could be positive. Nonetheless, this is our range equation.